Hello everyone, welcome back to the course on measurement and instrumentation, and today is the second lecture of our 9th week. Today we are going to continue our discussion on op-amp, and in the previous class I hope that you have developed the basic understanding of op-amp. Today we are going to start with the feedback in op-amps. Okay, so all of us know about feedback. Feedback is the process of feeding a portion of the output signal back to the input. Okay, you might have learnt about it in a course of control system, or if you have not learnt, you must be studying that in more detail. Okay, and it is the most important concept even in the op-amp circuit. Forget about other dynamic system. Okay, it is very important concept in op-amp circuit because it controls the gain. The process of feedback controls the gain. Okay, it improves the stability, particularly few kind of feedback is very important for the stability of the system. Okay, it can help you in reducing the distortion, and it can set the bandwidth. Okay, usually we have two kind of feedback, that is positive feedback and negative feedback. If I say positive feedback, you can see this diagram showing a positive feedback. You can see that the output here is fed back to the non-inverting terminal of this op-amp. Okay, so this is, if you remember, we have discussed the inverting and non-inverting terminals in the previous class. Okay, so output in the positive feedback is fed back to the non-inverting terminal, and this feedback is in phase with the input signal because this is the non-inverting terminal. Okay, so the inverting input remains disconnected from the feedback loop and is free to receive any external input voltage. Okay, now say it receives a 0 volt at the inverting input. The output voltage will be governed now by the magnitude and polarity of the voltage at the non-inverting input. Now say at the non-inverting input a positive voltage is applied. Okay, the op-amp output now will be more positive, and this will be continuous feeding back again to the non-inverting input. So the feeding itself also is a positive voltage because the output is changing in the positive direction. Now in this case, this will result in a full positive output saturation. So now the op-amp will, if you remember, we have seen the saturation and the linear region of operation in our op-amp. Okay, so now it will be in the positive output saturation. Okay, now similarly, say if the voltage on the non-inverting input is made more negative, the op-amp's output will also follow it and will become more negative. Now the feedback is again to the non-inverting terminal. Okay, and this will result in full negative saturation. Okay, so in one case you are achieving full positive saturation, while in another case when you are feeding a negative voltage you are achieving a full negative saturation. Means that if you see, the output in this case is a bistable operation. Okay, or bistable output. Okay, so it is stable in one of the two states, either in the positive saturation or in the negative saturation. Okay, so once it has reached, say, one of these saturation states, say for example it has reached to positive saturation, it will tend to remain in that particular state till we apply certain positive or negative voltage at the other terminal. That of course we are not going to discuss in detail, but you can understand that in this positive feedback the op-amp works in a bistable region. I mean, it will not be stable throughout the linear region. Okay, and therefore this kind of feedback is used when we want a switching kind of behavior from one point to another, or one state to another state. Say for example in case of comparator, or say Smith trigger, or say in oscillator, in those cases you will see that usually use a positive feedback. Okay, then we have a concept of negative feedback, which is very important for the op-amp operation, and particularly in this course we will mostly go through the negative feedback. Okay, so in negative feedback, the signal at the output, which is out of phase with respect to the input, is fed back to the input. Okay, the two signal at the input of the system now get subtracted, and the difference, which is sometimes also called error signal, is fed back. Okay, so as you can see that here the feedback is at the inverting terminal. This is your inverting terminal. Okay, so as V in increases, V out will increase according to the differential gain. Okay, So now differential gain is playing very important role, and we'll see that how this op-amp can also be used as a differential amplifier in this course. Okay. However, as V out increases, that output voltage is again fed back to the inverting input. Okay. Now this will decrease the voltage difference between inputs, which will subsequently decrease the output. So here in this negative feedback, if you see, output is decreasing. Okay. This will ensure that for any given voltage input, the op-amp will output a voltage very near equal to, or at least it is approaching the input voltage or V in. Okay. Now the circuit in this case will quickly reach a point of stability where the output voltage is just the right amount to maintain the right amount of differential input. Okay. So negative feedback is important for self-stabilizing system, and you will see that all the negative feedback op-amp circuits that we'll discuss here will be stable. Okay. Because of this, negative feedback configuration gives the op-amp the capacity to work in its linear mode, which is also known as the active mode of op-amp, as opposed to only saturation regions that op-amp can operate in case of positive feedback. Okay. So in fact, this feedback automatically reduces output error and stabilizes the system, which improves its accuracy, it improves the linearity and control of gain in all kind of electronic circuits, including the measurement and instrumentation circuitries. Okay. So there are two important golden rules associated with the op-amp, okay, particularly when it is configured in a negative feedback arrangement. Okay. First rule is that the op-amp input draws approximately zero current, means that your input impedance is so high that it is not allowing it to draw any current. Okay. And second important rule is that the op-amp output adjusts itself to make the voltage difference between the two input nearly zero. Okay. Of course, this has to be done within the supply limits. Okay. We'll understand it in more detail. Okay. Say for an op-amp, say I have a op-amp, I'm not showing the feedback and other things. Okay. You have one input at say V negative here. Okay. So you have V negative, and at another terminal say you have V positive. Okay. Say this is at inverting terminal and at the non-inverting terminal. Okay. Now your output is say gain multiplied by the differential input V positive minus V negative. Okay. Now since this gain is usually very high, of the order of say 10 power 5 to 10 power 6. Okay. So for the output to remain finite, this V positive minus V negative is almost 0. Okay. So the differential input V positive minus V negative is approaching to 0, or V positive is almost equal to V negative, and this is known as the virtual short. So whatever configuration it will have, we'll see that these two terminals are at the same potential, and this is a concept of virtual short. Okay. And now let's use this when the op-amp is operating say in case of a non-inverting mode. So this is typical example of non-inverting mode of op-amp. You can see that there is a feedback resistance fed to the non-inverting terminal, and one resistance R1 is connected, and the supply here is given to the non-inverting terminal, or V in is equal to V positive in this case. Okay. So from this, the rule that we have seen, this V positive should be ideally equal to V negative. Okay. So say you are applying input voltage, or you are giving input voltage to this non-inverting terminal, then also the same potential is appearing here. Okay. And V negative is equal to, V negative is also equal to V in. Okay. So you have V positive equal to V negative is equal to V in this case. Okay. So the inverting input here can be simply calculated by simple voltage divider rule, and if you consider this output V out, V negative can be given as V out into R1 by R1 plus RF. Okay. So due to negative feedback, we have already seen that V positive is equal to V negative, and V positive is equal to V in. So V negative is also V in, and V negative. So if I replace this V negative with V in this equation, I can write that V out by V in is equal to R1 plus RF by R1, or this is equal to 1 plus RF by R1, and this is closed loop gain of this kind of non-inverting mode of operation of this op-amp. Okay. Now, in this case, say for example, if say this input in place of getting applied to this non-inverting terminal, now if I am applying in this inverting terminal, now the op-amp is operating in the inverting mode. Okay. So, it is operating in the inverting mode, and again using the same analogy, okay, you can find the closed loop gain. Okay, and closed loop gain will be, in this case, will be equal to minus Rf by R1. All right. So, V out by V in this case, in the inverting mode, in the case of inverting mode, will be equal to minus Rf by R1. So, what I have done is, right now I have utilized the two golden rules that I have seen for the op-amp, okay, and particularly in the negative feedback state, and used it when it is operating in the inverting as well as in the non-inverting mode. Okay. So, one important application of this kind of feedback circuitry is in the voltage follower mode, okay, which is also known as isolation mode. Okay. You can see that here what I have done is, from the non-inverting mode, what I have done is I have just removed the feedback resistance, okay, or I have kept Rf equal to 0. So, in this case, V out is just following the input voltage, or V out is just equal to V in. Okay. So, the voltage follower therefore possesses some of the important characteristic. It has a very large input impedance or input resistance. The setup has unity gain, and you will find that there are a number of applications of this voltage follower, okay, where you require high input impedance, but say gain should be equal to 1 or very near to 1. Okay. So, it has a very large input impedance, it has a unity gain, and it has a small value of output resistance or output impedance, because this is again a configuration of op-amp. Okay. So, when an op-amp is used as a DC amplifier, it is important that output should be at 0 for 0 DC input voltage. However, this is not always true. In actual practice, a small DC output voltage will appear even when there is no input, or input is 0, and this voltage is known as offset voltage. Okay. The output offset voltage in an op-amp arises due to 3 key parameters specified by the manufacturer. These 3 important characteristics or 3 key parameters are input offset voltage, input offset current, and input bias current. Okay. Let us see these 3 parameters which govern the output offset voltage. First is the input offset voltage. Okay. So, this happens because of a mismatch in the base to emitter voltage of the input differential transistor amplifiers in case of the op-amp. Okay. And this causes the DC offset voltage at the output. Okay. So, manufacturers specify the input offset voltage, mostly represented by VOS, as required input to the op-amp, such that the output voltage is at 0 stage. Okay. So, when an op-amp is used as an inverting or say non-inverting amplifier, it will have a DC output offset voltage due to VOS, and this output is given as VOS into your closed loop gain that you have just seen, say 1 plus Rf by R1. Say I am calling this as beta. So, 1 plus Rf by R1 I am calling a feedback factor beta. So, output offset voltage is equal to this input offset voltage by beta. So, if you know this value, you can at least minimize this value. Okay. Then second important aspect is the input bias current. Okay. And again, it is also arising from the differential amplifier stage. Okay. So, for proper operation of the operational amplifiers, a DC bias current must be supplied to the input differential amplifier stage, and this current is of the order of say certain picoamp to certain nanoamp, and there are since 2 stages. So, I have 2 bias currents, IB1 and IB2, and bias current is basically average of these 2 currents, IB1 plus IB2 by 2. Third important characteristic that we have seen or parameter is the input offset current, and again it can be calculated from here only. So, if IB1 and IB2 are the 2 bias currents, input offset current can be given as IB1 minus IB2. Basically, it is the difference between the 2 input bias currents. Okay. So, the 2 input transistors forming a op-amp are not perfectly matched, and our differential bias current is required at each input, and difference between the two bias currents is actually your input offset current or IOS, and it is given as we have just seen as IB1 minus IB2. Okay, so this is in a very nutshell what is op-amp. There are certain courses like analog electronics where you can learn in detail about op-amp. So there are different modules specifically dedicated for the op-amp. Right now we are just discussing it so that we have the basic understanding that how these op-amps can be used to develop different circuitry. Say for example, one of the important utilization of op-amp in a circuit used in instrumentation is say inverter. Okay, so you can see the basic configuration of inverter. Okay, again op-amp is used. So the feedback resistance in this case, this RF is used in such a way that is equal to this R1, okay, which is connected to the inverting end of the amplifier. Okay, so when you have this feedback resistance R1 is equal to the R1 resistance, in this case if you remember, your output is equal to V out is equal to minus RF by R1 into V in. Okay, say I am calling this input Vn is equal to V1. Okay, in this case what will happen is when this RF is equal to R1, then V out will be equal to minus R1 by R1. So V out will exactly be equal to minus V1. Okay, so you can simply see that the output voltage is just 180 degree out of phase with the input voltage, or this V out is equal to minus V1. All right. So this is perfect inverter that you have just designed using a op-amp and simple resistances. Okay, you can also use it for developing adder. Okay, so you can see adder made using a op-amp. Say you can have n number of resistances here. Okay, so say this is I am calling V in n. Okay, so R1, R2, R3, R4, you can have number of inputs, and then output here will be equal to minus RF by R1 into V in 1 plus RF by R2 into V in 2, RF by R3 into V in 3, and so on. Okay, and of course a negative sign persists. Okay, so if all resistances are say equal, RF is equal to R1 equal to R2, R3 and so on, the circuit acts as a pure adder and the output voltage equals the sum of the input voltages. Of course, negative sign will still be there, and output voltage will be equal to say in this case say this RF is equal to R1, so this term will become 1. Okay, similarly other terms also will become 1, and output voltage will be equal to minus V in 1 plus V in 2, V in 3 and so on. Okay, similarly you can use it to make a subtractor. Okay, in say this is one of the example of subtractor, and you can see that this is a first op-amp, this is the second op-amp, and using different resistances in different configuration you can use it to develop op-amp. So first input is here and second input is here just before the second op-amp, and the output voltage in this case can be given as minus V in 1, V in 1 RF by R1 into RF by R3 plus V into RF by R2. So what I am doing is the output from this op-amp is fed back to this, and now it is again, if you see this stage acts as a simple adder. Okay, so this is a two-stage subtractor, but again you can have different stages op-amps also, and you can also make it using different circuitry. So in this case, say for example, if RF is equal to R1, R is equal to R2 is equal to R3, again in that case V out will be equal to V in 1 minus V in 2. Okay, but if you see here, you are not having any gain, but if you want to have a subtractor with gain, you can use a different circuit. Say for example, this is one of the circuit that you can use as a subtractor with certain gain. Okay, so in this case, say RFN is gives the negative feedback and sets the gain, while this RFP grounds the positive input to stabilize the op-amp, and the output voltage in this case will be equal to RF by R into V in 2 minus V in 1. Okay, so you have a gain as well as the difference. Okay, so I mean, according to your need, you can change the circuit and you can design your own circuit for your instrument. Okay. Similarly, it can be used for multiplier and divider. Say for example, again a simple circuit in this mode. Okay, you are using inverting mode, and the output voltage in this case can be simply written as minus Rf by R1 into V in 1. Now this case or this circuit can be used both as a multiplier and a divider depending on what you choose as Rf and R1. Okay. In case Rf is greater than R1, the circuit in this figure acts as a multiplier, and if you say change it, say now if Rf is less than R1, in that case it acts as a divider. Okay. So let's take one example to understand this. Okay. So consider that Rf is say 10 mega ohm and R1 is 100 mega ohm. So V output is equal to minus Rf by R1 into V in 1, and since Rf is 10, so you have minus 10 by 100 into V in 1, and this V out is equal to minus V in 1 by 10. So therefore the input is now getting divided by a factor of 10. Okay. Now consider another case where Rf is equal to say 100 mega ohm. Okay, and R1 is now say 10 mega ohm. Alright, in this case V out will be equal to minus Rf, which is 100, okay, divided by R1, which is 10 into V in 1, right. So in this case V out is equal to minus 10 V in. Alright. So now you are actually input is getting multiplied by 10 to get this output. Alright. So just by changing the Rf and R1, or just by swapping them, you are able to generate multiplier and divider respectively. Okay. Similarly, they can be used for other mathematical operations also, like for integrator. You can use op amp to develop an integrator. Just see that you are having a capacitor in the feedback and this R1 is there in the input terminal. So in this case, the output here is equal to minus 1 by RC into V in 1 into dt. Okay. Similarly, you can use it for as a differentiator, and when you are using it as a differentiator, so now you just swap the capacitor and resistor, and if you are using capacitor at your input and R in this feedback, V out is equal to minus RC into d by dt of V input. Okay. Then you can use it for comparator. You can see that in this case, I mean everything is similar, but this A minus AV, or sometime we call it minus AV OL. Okay, this is very high as compared to the op amp, and you can have output, you can have minima and maxima depending on the signal that you are using. All right. So you can also use it for logarithmic converters, like this is one example. By using a diode, you can in this feedback you can use it as a logarithmic converter, and in this case V out will be equal to 1 by beta, where beta is a constant, exponent constant, into natural log V n minus 1 by beta log into f naught, which is again a constant, into R1. Okay. So you can have more detail in your textbooks. It's impossible to discuss all these circuits in more detail here, but what I wanted to let you know that these are some of the circuits that you can develop using op amp, and they are useful in instrumentation, but these are just small number of circuits that I am just going through. You can have n number of circuits or n number of mathematical operations performed by using op amps. Okay, right now I am using 1 or 2 op amp. You can have multiple op amps to generate all these things. Okay, another important application of op amp in instrumentation is to have a differential amplifier. Okay, just have a look. This is a differential amplifier, and in this case V out is equal to AD into VD, where VD is your differential input and AD is the differential gain. Okay. So when they are equal, the output voltage will be equal to 0. Okay. Now this is very important, particularly to reject noise, and for that you have to understand one important concept of CMRR, common mode rejection ratio. Okay. So if you see, you have two gains, one is common mode gain and another is the differential gain. So common mode gains tells you that how much the amplifier respond to noise or when the same input is applied to both terminals. Right now I am assuming that same noise is appearing at both the inputs. And differential gain, AD, gives you an idea that how much the amplifier amplifies the actual signal difference. Okay, and we are of course more interested in the AD. But the important concept here that I just wanted to mention is the CMRR, or common mode rejection ratio, which is the ratio of AD to AC. Okay, so it is the ratio of the differential gain to the common mode gain. Okay, so you want this common mode differential gain to be as maximum as possible, and this should be minimized. Okay, or if I say CMRR is mostly represented in dB, and CMRR is equal to 20 log 10 AD by AC. All right. So a high CMRR, what it will signify, that it will tell you that desired differential signal is now strongly amplified, or in other way you can also say that since it is equal to CMRR is equal to AD by AC, so a high CMRR does not only mean that it is AD is maximum, but it also says that this AC is suppressed, or the common noise at both the inputs is highly suppressed. So usually you want a CMRR to be very high. So if you remember yesterday's discussion, I have mentioned a term that CMRR for ideal op amp should be infinite. Okay, so an ideal differential amplifier will have common mode gain or noise signal gain as 0, and differential mode gain as certain finite value but very high, and that's why CMRR is actually infinite. All right. Again, if you want to use this op amp in conjugation with a certain transducer, I think we should discuss one of the example, okay, how we can use it in conjugation with certain transducer. And this is one of the example here. You are using a capacitive transducer. Okay, so capacitive transducer is attached in the feedback here, and in this case the output voltage is given as minus CIV VI divided by epsilon A into X, or if I consider this as a constant, V out is equal to some constant into X. Okay, so this is a capacitive transducer, say for example for displacement measurement, and with the displacement, say with the change in X, this V out is changing because this capacitor value is changing. Okay. So you can also use it for different purposes, like for developing charge amplifiers. Okay, we know that there are different transducers which gives output which is in terms of say charge, and to feed it to next stage you want to convert it to certain voltage value or some current value so that it can be fed to the next stage. Okay, so one of such example is say like a piezoelectric transducer. So the output of a piezoelectric transducer is say charge. We have already seen that. Okay, now this charge is converted to voltage, and this has led to development of a specific kind of amplifier known as charge amplifier. The charge amplifier offers several advantages that over a usual voltage amplifier for this kind of application, and usually that's why charge amplifiers are exclusively used for piezoelectric transducer. One of such example is shown over here, a piezoelectric transducer and op amp for in conjugation to each other, and this is a kind of charge amplifier that we have. Okay, so in this case you can see that V naught is equal to, or V naught by Vi can be written as say minus Cp plus C cable by Cf, where Cp is your capacitance due to this piezoelectric transducer, and C cable is the parasitic capacitances because of cable and other things. Okay, and Cf is your feedback capacitance. I will come back to this resistance later on, but right now I am considering only Cf. Okay, so V naught by Vi is equal to minus Cp plus C cable by Cf, or say I am calling this Cp plus C cable as say C. Okay, in that case V naught is equal to minus C by Cf into Vi. okay, or Vi, since it is equal to, this is a piezoelectric transducer, so, or capacitor also, so Q is equal to, you know, that is equal to Cv or Cvi in this case. So Vi is equal to Q by C. So in that case, V naught is equal to minus C by Cf into Vi, and if I replace this Vi with this value, okay, I will have V naught equal to minus C by Cf into Q by C. Okay. So just rearranging all these things, you get V naught equal to minus Q by Cf, and Q that is generated here is, we have already seen for the piezoelectric transducer, it is Kq Xi by Cf, and this is how your output voltage is now connected with this Xi, okay, and there is no charge term here. So you are having this term free of any Q value, okay, and the output what you are getting here is in terms of voltage, okay. So it indicates that the output changes instantaneously with input without loss in the steady state response, and that's why we have seen that piezoelectric transducers are mostly applied to dynamic systems rather than in the static systems, because charge will be lost immediately, okay. However, this is also not practical. This is because the operational amplifier does not have an infinite input resistance, as we have already assumed, okay. So the input resistance and the leakage resistance of Cf exhibit a steady charging of Cf by the leakage current till the amplifier is saturated. To overcome this problem, a resistance Rf is connected across capacitor Cf in the feedback path, and this is exactly the resistance that I was talking earlier, this Rf value, all right. So this Rf is connected here to avoid these things, okay. So Rf is connected across capacitor in the feedback path, and this will prevent a small leakage current from charging the capacitor heavily, okay, and this will give you more control over the charging of the feedback capacitor. All right. So these are some of the applications of op-amp, and one important and very crucial application of this op-amp is in the development of instrumentation amplifier, and in the next class we will discuss about how this multiple op-amps can be used for the construction of instrumentation amplifier, and what are the important advantages of using instrumentation amplifiers in this for the signal conditioning. And you will use, if you are working for certain system development, you will definitely use instrumentation amplifier at various stages, okay. So we will be discussing a special class of amplifier, that is instrumentation amplifier, in our next class. Thank you.